In this lesson, we're going to have a little look at how our understanding of acids and bases has changed over time. Records show that the ancient Greeks knew about acids and bases. They classified them according to their taste, and they said these things are sour, so there are sour things like vinegar. And they used the word aceto. And then they had things like bitter things. And they didn't know as much about the bitter things, the alkalis or the bases, but they knew that soap was bitter. And we know that the alchemists, so moving on through times into sort of medieval times, the alchemists, they used things like soda, potash, ammonia, hydrochloric acid, sulfuric acid, aqua regia, which is a mixture of nitric acid and hydrochloric acid. And we know that they were fully aware of some things were acidic and some things were basic, but they didn't have much of an understanding of the theories around them. So our understanding of acids and bases didn't really change that much from medieval times. You may have heard of the theories of phlogiston and how phlogiston was replaced by oxygen. And there were some ideas around that things that had, once the phlogiston had gone from them, that they became acidic. And then when the idea was replaced with oxygen, actually, there was a lot of ideas that oxygen led to things being acidic, which even leads to, in German, the actual word for oxygen is Sauerstoff. But this we now know is wrong. Ideas didn't really progress until the late 19th century when this guy came around. So this is Svante Arrhenius. Now, Arrhenius is a Swedish chemist, and he was a bit of a heretic. He came up with ideas that the other people in chemical society didn't really agree with. He said, and he was the first scientist to kind of postulate this, that acids dissociate in water to produce hydrogen ions, and that bases dissociate in water to form hydroxide ions. Now, this is very much the idea you will have covered at GCSE. And although he was considered a heretic and people disagreed, in 1903 he actually got the Nobel Prize for chemistry for these ideas. Now, not that long after, we get these guys, and these are the two that you really need to know about at A level. So this is Johannes Bronsted, and he was a Dane, so another Scandinavian. And then this guy is Thomas Lowry, and Thomas Lowry was based at university in England in Manchester. Now they came up to both working separately, but around the same time, so their ideas are known as Bronsted-Lowry acid-base theory, and they were a little bit after Arrhenius, but not too long after, and they came up with the idea that acids are proton donors. Okay, proton donors. So if we consider our acid as being HA, where A is the rest of the molecule and H is the acid, is the proton, and they can form H plus, so a proton. If you think about what a hydrogen ion is, it is a proton, plus A minus, which is the acid with the hydrogen removed. And the bases are proton acceptors. So a base is something that is able to take a hydrogen ion off of something else. It's able to accept a hydrogen ion. So generally it's going to have a lone pair of electrons that the hydrogen ion is going to be able to form a dative bond with. So we would simplify that if we use B as a base and we add to that a proton or a hydrogen ion, then we form Hb+, and that would be acting as a base. Now there is another guy called Lewis who has another different theory on how acids and bases work, and he was actually working a very similar time to Bronsted and Lowry, and this is Gilbert Lewis. Now, Gilbert Lewis was an American. He was at Berkeley in California, and you might know Lewis's ideas more commonly because he's actually the guy that came up with dot and cross structures. So I'm just drawing you the dot and cross structure for ammonia here. So Lewis, very famous for his dot and cross structure. So he was really into like lone pairs of electrons and these ideas. And a Lewis base, and I'm going to start with a base because it's easier to explain, is something that has a lone pair of electrons, a bit like a nucleophile. And that lone pair of electrons is able to accept things bonding to it. It's able to form a coordinate bond. So, and a Lewis acid, and it doesn't have to be a proton, but protons do, hydrogen ions or protons do this. A Lewis acid is something that accepts a lone pair of electrons in the form of a dative or covalent bond. Now, you don't really need to know about Lewis bases for your A-level. You need to know about Bronsted-Lowry theory, but I've included it because you might find information about it on web pages or in various textbooks. You might hear about Arrhenius acids or Lewis acids, so I thought it was worth just mentioning all the different theories. If you go on to do chemistry at university, you'll find out more about Lewis bases and Lewis acids. So let's have a little look at Bronsted-Lowry acids and bases in a little bit more detail. So let's remind ourselves, so acids are proton donors. So by proton, if you consider a hydrogen ion, so if a hydrogen atom has got one proton and one electron, if we remove the electron and make it into a hydrogen ion, then it is just a proton. So we refer to hydrogen ions as protons. So acids are proton donors, bases are proton acceptors. So molecules that are able to take a proton. So if we have a look at what's actually happening, we can see, so if we consider we've got, this is our A, our acid molecule, so H is the proton attached to the rest of the molecule. The A could be ethanoate, it could be chloride, it could be sulfate, okay, and we're going to react that with B, which is our base. And what we do is we actually end up, we form A, which is minus, and we get HB becomes HB plus because it has got the hydrogen now on it. Okay, so now some terminology you've possibly not seen before then. So our acid has a conjugate base. So once it's lost its proton, it then becomes a base because it could regain that proton and turn back into an acid. So we call this an acid conjugate base pair. And our base, once it gains the proton, becomes an acid. So we call it a conjugate acid. It's the conjugate acid to the base. So they are a pair because when it gains, so without the proton, it's a base, but once it's gained the proton, it's an acid. And it can turn back into the base and so forth. Now, because our protons can move backwards and forwards across the acid-base pairs, it's actually more correct to draw the arrow as a reversible arrow than it is as a straight arrow. So now let's have a look at what happens when acids and bases are put into water. Now, water's really special, because water is amphoteric. So you might be saying, well, what does amphoteric mean? It's the same root as amphibians. So amphibians can go on land and on water. So water is amphoteric because it can behave as an acid or as a base. The word comes from the Greek amphora, and an amphora would be a sort of water vase or wine vase that's got two handles on it. So it's got two handles. So there we go. So, and this is why we call it amphoteric, because it can be both acid and base. So we're going to have a look at what happens when we have water acting as a base. So when an acid is added to water and it acts as a base, and then we'll have a little look at what happens when water acts as an acid, which would be when it has a base added to it. So if we take an acid, which we're going to call HA, remember the A stands for the rest of the molecule, and we add it to water, what happens is we get an equilibrium formed where we get A minus, so that would be the conjugate base of the acid, and we get H3O plus, so the oxonium ion, which is often simplified just as a proton, but you need to remember whenever you see H plus just as a proton, aqueous, it is always going to be going round attached to a water molecule. We can also see what happens when water acts as an acid. So if we add a base, which we're just going to give the generic symbol B to water, H2O, then we're going to get another equilibrium set up, and we will form HB plus, so the protonated base, which would be our conjugate acid, and the hydroxide ion. Okay, so we can see that water can act both as an acid and as a base. So here's just a little reminder of structure of water. So it's with the two hydrogens and normal covalent bonds, and then it's got lone pairs. When it gains a proton, that goes on with a coordinate or dative covalent bond. One of the lone pairs is able to donate both to the proton, to the H plus, and therefore it forms the H3O plus.